time frame.
Yes, you are.
All right. Hello, and welcome to our final lecture. We're going to be talking about time recovery and packet synchronization. First, some announcements. Sorry for not showing up to office hours today. Something came up. I will be in the lab tomorrow, Friday. Yeah, I don't think this is going to go up before Friday, so it doesn't matter. And then assignment 6 due Sunday. Let's give you guys a little extra time. And assignment 7 will also be dropped Sunday. And after that, your link simulation will be complete, and that'll lead to next quarter, and we'll start putting stuff on microcontrollers. So we are basically in the final stretch. Speaking of the final stretch, RAP is coming to a close, and as a lead, we'd like to see this project continue. And so if you're interested in running for a lead, let us know. That'll probably happen around week 3 to week 5 next quarter, the interview process to actual elections. But if you're interested, please let us know. We'd be more than happy to talk to you. And yeah. First, I'd like to begin with some pointers on assignment 6. Just some trends which I think are important to see. So a lot of people had trouble tuning their Ki and Kp values. And honestly, tuning it is just like, you just throw something at the wall, see if it sticks. But there's like a little intuition behind it. First, I would recommend you tune without any frequency offset and channel filter. And you can start with values I listed. But the main intuition to look out for is you guess a value, and then you can modify certain values. So say like I guess this, a Kp of 0.1 and a Ki of 0.001. And okay, for this Kp, let's see how it changes when I change Ki. And so I increased Ki to see what happens, and it condensed. And so that's the opposite of splitting into 2 balls, and so probably don't want to go in that direction. So next thing I did was increase Ki, or Kp I mean, because hopefully this will get us in a better direction, and now we have a split, 2 clumps in a way. And so this is kind of the more right direction, and so knowing Kp was around here, I increased Ki a little bit, and we have nice clumps over here and here. And that's where our points should be, around 1 and -1. So that's more in the right direction. And if you try and increase Ki again, it condenses. And so we increased it too much. So we found a Ki in a way. Let's try and tune the Kp. And that's the kind of process which you could try and do if you haven't done the assignment yet. But yeah. The next thing to talk about is normalization. And so first, we implement the entire simulation with no channel filter, and it has the amplitude is a certain value. In this case, this is no channel filter, or this is actually before the channel filter, an amplitude of like 0.13 to 0.17, somewhere around there. And we're tuning our Ki and Kp values around these according to an error function with this amplitude. If we tune it to that amplitude and we put in the channel filter, the magnitude is going to be significantly less. Right? We see over here it's got a magnitude of at most 0.02, which is a tenth of the original magnitude. So it's going to be significantly, so your Ki and Kp values will not work, which is why we do this thing called normalization a little bit. So actually, before I talk about that, to demonstrate how much it changes, it's a squared term, right? Because when you create your error function, you have x times a cosine and y times a cosine, low pass, and those have their own magnitude a. Multiply that together, that creates a squared. And so that's a little mathematical justification of how your error function changes, right? if your magnitude changes from a squared from 0.13 to 0.001, you have a decrease in your magnitude by 100 times. And so it's not gonna move. It's not gonna keep up with your phase as well. So you can try like, I dropped an announcement, but you could try y equals the original signal over the mean of the absolute values. That's like, it's one way you can do it. It's an L1 norm. And then what you want to do is you're going to plot to see, is this new value, normalized value, the same magnitude as what you tuned it to? If it's not, then just like divide it, just scale it. Just scale the value until it's the same as your original magnitude. And then your Ki and Kp values should work, the original ones. And this is actually really important because you're going to have your receiver at different distances from your transmitter. And at different distances, it's going to have different magnitudes because it attenuates as it goes through the channel, meaning our air. And so having this keeps it consistent. So you don't need to modify your Ki and Kp values each time you change the distance. Okay, next thing I'll talk about is frequency offset. So this part over here is, I implemented some frequency offset and I plotted the phase. And what I mean the phase is, in our cosines loop we have a theta, and that theta is, it's like the theta we adjust to match the phase of our input signal, right? And so the theta creates like a ramp function but negative, okay? And a good question is, does this make sense? And if it does make sense, can we go the other way and say, how can we validate our own system, right? We know that the change in phase between the component that you're the input signal and the cosine or sine that you're modulating with can be expressed as the difference in frequency, right? Fc minus Fr. And then in turn, the change in theta each iteration is the difference in frequency times the time step in between. And so if this were to match up, if we were to validate without knowing our cosines loop works, that this works, the slope of this should equal our delta theta, right? Because this is how our slope changes every iteration. It's a line, it's constant, and that's what delta theta is. Okay, so yeah. Another thing to notice also is that this is a ramp function, and we're implementing a control system on it. And the control system, even though you're tracking a moving offset, right? Even though it's moving away from you, the control system works quite well for like even like a 50,000 hertz to 100 kilohertz offset. And so that tells you that this system is pretty rigorous. Okay. That being said, let's hop into the main part of today's lecture. Can you turn that again? Okay. So we've simulated noise in the channel, right? Distortions. But we still have one main assumption left that we're not accounting for, and that's we assume that the first index in our data is the first symbol. We don't know when the first symbol is. We don't know when it occurs. And yeah, so we're gonna try and deconstruct this. And the first way where we're gonna start is actually we're sort of sampling. See how does sampling, the shortcomings of sampling. So if you guys recall, we use a root raised cosine filter. And the root raised cosine filter is designed to tackle this one problem called intersymbol interference. To draw the root raised cosine filter, that looks like a sink, right? Okay. This is in the time domain. Call it h of t. Okay. And so the point of it is that you have, when you convolve your root raised cosine filter with your symbols, which will be a delta train, when these pulses are all put together, you get basically this. Look at the first filter, first symbol. It'll be like that. And then the second symbol is up. And draw this more accurately. Second symbol will be like this. Third symbol will be like this. So the zeros, so when it's not on the symbol that your filter is being applied to, on the ones that's not being applied to, it equals 0, right? So these values, your ones and negative ones, generated from your delta train, are still the same. They're not distorted when you convolve all the pulses together. But this is on an analog signal. And analog signals, well, actually on a microcontroller, we're gonna have to sample it because we don't have infinite memory. It's gonna be a discrete signal. So the samples we may see on the discrete end will look something like this. Say we have, suppose this is our incoming signal. Right, something like this. We're gonna be sampling at some arbitrary start time. And marker going to so if you sample at the same rate as your symbol rate, you can get information like this, right? Where you're no longer at the peak, and therefore you're getting interference from other symbols, right? If you sample on the left side, for example, you can be right here, right? And that's not ideal because now we don't have a more clear picture of our of the signal we're sampling. As you could probably guess, a pretty clear solution to this would be to increase your sampling rate. So you can have more points to pick from. They may not be at the peak, but you can always pick the point that's closest to the peak. And that will approximately give you the right answer. All right? And we actually do this in our code, right? We generate the signal and then we upsample it to 1 megahertz. So 50 kilohertz is our main, as the frequency of our information, the frequency our information is being transmitted at, and 100 kilohertz, or 1 megahertz is what we're sending the wave at, right? So we get around this, and we can actually describe this, if we wanted to, mathematically as follows. Is this still on camera? Yeah, okay. So you could say on the sampling end, you have, we'll do it in continuous and we'll turn it into discrete. Equals the summation of your symbol. So it's S of t is either in the set of -1, 1, times it's delta of t minus lt. Convolved with your pulse filter, the channel, the receive filter, and there's also noise introduced in between. So we'll call that the noise W, and the receive, and on the receive side, it's W convolved with the receive filter. We can simplify this to, let's call it H of t, because this is the whole channel. And then, don't need to worry about that. And what you get in more simpler terms is summation of this times H of t minus IT. Right? Delta convolved with the filter is that. And from here, we can do a little analysis. Let's see, what would be the best way to put this? So we have a delay, an arbitrary delay in this. So we can now call this x of t plus tau. Okay? And then we're going to discretize it, because this is how we're sampling. To discretize it, we'll call it x of kt, which is our sample number, t, which is the symbol period, which is t is equal to, for example, 1/50 kilohertz. And m, or SPS, what are you going to call it, which is going to be your oversampling rate, how many samples per symbol we have. Then I'll plus tau, and then of course this equals the summation of S of kt over m plus tau, h of, same thing, kt over m plus tau minus it. Right? And so looking at this, we can see that, of course, if tau equals 0, we have no problem, right? We'll be sampling sampling the right points. And again, if tau equals some integer multiple of t times m, then this equals summation of s of, call this t, k plus l over m, h of t, k plus l over m minus t. All right, and so I can equal an integer value, and so say if I equals k plus l over m, right? When this is an integer value, you recover, of course, the same symbols. And then by having many symbols, many samples, you could say that there's a value where I is approximately k plus l over m, and therefore our information should be recovered, right? Because this would be s of that value times h of about 0, which is going to be, this should be your raised cosine, right? The total channel. Let me reiterate that. Your pulse is a root raised cosine, as we mentioned, as we've discussed before. Channel is some random distortion, and then your receive filter is also root raised cosine. And so this should be about, if you have no channel distortion, a raised cosine. Okay. Should fix that. And so your information's about recovered. And so that's like a mathematical justification of why we'd want to also sample a lot. Okay. Thing is, fortunately, that's not our only issue. Can you check? So that's not our only issue. You could think about this also in the physical world, where we have our antenna, so our transmitter, and then send some signal, and then we have our receiver, and okay, so that means there's some delay, some delta t that happens, and we know that from before, if tau equals some integer multiple of your period over your oversampling rate, then our information is recovered. So we could say that delta t equals some integer plus another small offset, right? And then now, if this is moving away at some velocity, then this is going to change, this tau, right? And you could express this tau as some initial tau plus the velocity of the receiver over the velocity of the signal. Signal, then receiver, I don't know how to spell receiver. That looks wrong. Receiver. Times delta, times time, right? You can work out the physics for that if you want, okay? And so what actually happens with this is we get a timing delay, which is now a ramp function. And we know that from previous assignments, we know control methods which can easily track a ramp function. So this problem isn't too bad, I guess. We can fix this. Another problem to talk about is also internal in your hardware. You have microcontroller 1, which has its own definition of a 1 megahertz signal. We'll call it MCU 1. Let's see, we're talking about 1 megahertz, and it could be omega r. Like if we have some actual absolute value, if we have an absolute understanding of what 1 megahertz should be, and this is not perfect, we'll call it defined like this: omega r, and I'll call it omega 1. And MCU2 has omega 2. And what this means is that this creates samples at this rate, at omega 1 rate, and MCU2 creates or samples at omega 2 rate, right? And so if you were to draw this out, you could say MCU1 sends samples here. Keep in mind this is quite exaggerated, but for visualization purposes. And that could be the sampling rate, the rate at which our signal is dispensed, right? An MCU2 could have a sampling rate like this, or maybe it's a little bit faster. Right. So if this whole thing is, we have one symbol, so look how many of this? 1, 2, 3, 4, 5, 6, 7, 8. MCU1 could have 8 symbols per second, and then MCU2 could have 7. So this is also problematic, right? I might have counted wrong, but the rates at which, oh, it's actually 9. This also has some kind of offset, and again, you can mathematically model this as in, what did I say it was? Tau equals omega 2 or minus omega 1 times some time, which makes sense. And again, you can notice that this is a ramp function, a linear function, which again we can track through the control methods we discussed last time. And so, of course, this is very problematic because how you implement or currently downsample your signal in MATLAB is you say something like this. X, we'll call it downsample, equals X received or after some processing, and then you go from 1 SPS to the end. Right? And of course you can apply this if this is changing, your delay is changing, right? Your samples per symbol is changing from the difference in the microcontroller clocks or the movement of your 2 antennas from each other, or 2 transmitter and receiver. So this is also raising some more issues in how we pick the right samples. We could graphically demonstrate this. I could draw some signal, and we'll say it's like this. And it could be like, this is 1, 2. So here's your first symbol, or first sample to pick. And you got second. Right, so this is 3 samples per symbol between 1 and 2. This is 2. This is 3 again. All right, so that's like how you could visualize that if you were to, pick the best points. So we need some scheme to pick the right samples. Yeah. And so we can't measure what the peak points are. We don't know what the received amplitude is going to be. And so we can't check that, hey, this is a peak. This has to be the right symbol. This has to be a symbol. And furthermore, there could also be like a bunch of noise, spikes in noise, and if you do it based on a peak, then you're going to have some error value, or some values which should not be there. And so you can't check the frequency at which your peaks occur you can't check the peaks nor the frequency at which they occur to figure out where your samples are. But something you can do, I'm gonna erase this, is you can look at where your symbol intersects 0. To give an example, let's actually propose a control method real quick. Sorry, let's show this thing real quick. So in your communication system, we can argue that, okay, it'll be 3 samples per symbol, and it's gonna gradually, if it's going to change, it's going to gradually change, right? Because these offsets gradually happen. There's no jump in the delay or anything. It's continuous. And so one way is we can try and iteratively adjust, tune how many samples per symbol there are based off the frequency at which it crosses the zero mark. What does that mean? Okay. So you have your you have a signal like this. Okay. And you have peak values here, right? And these are all separated by period t, right? Write this out as t. Okay. Another thing you can argue is that this is also correct. The distance between here and here is also t. Okay. And we can easily figure out where a signal crosses zero, right? You can look at the sign of the previous sample and the sign of the next sample, and if the multiply the two together, take the sign, it should be negative, right? So we can figure out where it equals zero pretty easily. So we can use this property to try and tune our samples per symbol, because if we know this is also periodic, if there are 8 samples per symbol between these two peaks, there should also be 8 samples per symbol between these two peaks, right? And so the idea would be okay, well, clearly these peaks occur not every t. I mean, these zero crossings don't occur every t, right? Like right here, it might occur 2t, right? So it's not exactly the same method. But let's keep this property in mind, and I'll come back to it actually. Let's look at it this way. So revisiting the original problem, you have some delay, and the delay is a ramp function, and that's actually going to affect your samples per symbol linearly, because that's the frequency of this, but we'll stick with it. But we know how to track a ramp function, right? And so likewise, we know a good control algorithm for this. And we could say that our samples per symbol equals our old sample to symbol, plus k, a proportional component times our error, plus an integral component, right? And this is something that we implemented, right? And this control structure should work quite well for figuring out, the correct symbol. So in this case, the first question we need to ask is, what's our error function? Well, knowing that we can find these zero intersections and that they're periodic, we know that if SPS is right, then call it zero crossing. The first zero cross and the second zero cross. How do I write this out? We'll call it like this. Minus 0 cross 1. So the number of symbols, or samples between two consecutive zero crosses, so n and n minus 1, should be some modulus, some whole number. The modulus of it should be equal to 0. All right? If we do, if we have 8 samples here, there's 8 samples between these two zero crosses, and our SPS is 4, then we know we're okay. We know two symbols have passed, but their SPS is right. If it's 3, then we know something went wrong. Maybe now we're recording the wrong sample too early. We're recording maybe this sample now instead of this sample. So this, in a way, is like an error function, right? If we're off, then we have some value. If we're on the right point, it's 0. Okay. But of course, this encourages that we're always ahead, right? Because this is always a positive value. So you can, if you want, you can shift it by saying, hey, if the zero crossing, like this value is like this. Error for error times the Boolean equation of right, and so you can do this, and this would just shift your the modulus function, which operates from 0 to SPS in this case, to negative SPS over 2 to SPS over 2, right? And that should be, you can think about that, see how that works. An alternative framework for this would be to look at it like a circle, right? We know every SPS it's going to return to a symbol or some kind of zero crossing. So we could put it in actually the exact framework as the Cauchy's loop, where we talk about this in terms of phase and frequency, where SPS is our frequency. To demonstrate this, we could say that we draw a circle and say we start at this point. Every sample would be like taking a step along the circle and returning back to the original point, right? So if you were to describe every sample as a step around the circle, then you could say that, say this is the next point, and they're evenly spaced. This is equal to, we'll call it delta phase, delta theta, equals 2 pi over SPS, right? And so of course we can describe the current phase is equal to phase of M. Right, and this makes sense, right? Because after SPS steps, we've gone a total distance of 2 pi. And also a good motivation for this kind of framework over the modulus one is that we have nice functions in MATLAB to wrap it to pi, to wrap it to the range negative pi to pi. You just use the function wrap to pi or something like this. Say we'll call it theta, and that gives you from negative pi to pi some number in that interval. And that's exactly what we want instead of taking the modulus operator, which can be tough to implement in C. Or how would this be different? Well, I guess it's the same. There's no really difference, but I think it's nice to think of this as in terms of frequency. Okay, so let's try and stitch this together. We know that we have a zero crossing occur, and let's say we assume our zero crossing occurs at a phase of 0. Okay, then we can check, of course, that every time we go around, it should be at 0. Okay, and if it's not, we adjust. We also know from this kind of model when our sample should occur, because our zero crossing is actually right in the middle between two symbols. So if our phase starts at 0, then the point that should be sampled should occur at pi. Right? And that makes sense looking at a drawing of this. This is t, this is t, this will be t over 2. We'll call this 2t, we'll call it 3t over 2. Right? And so it would make sense that this is an even number of symbols away, or the half the number samples per symbol away. Right? Yeah. So we're gonna sketch out like some pseudocode for this. It'd be like, okay, let's go through samples 2 through n. And we could say current phase equals the last phase. Use theta. Theta of n equals theta of n minus 1 plus 2 pi over the current SPS. We'll call it m, so let me write this. 2 pi over m. And we say if, so if the point crosses from here to here, right, it may not always be exactly pi, then we know we have a correct symbol. We have a correct sample, right? So if theta of n is less than negative pi times some like margin, right? Or by margin I mean like it's within this range. So if it goes from here to here, it's within this range, then we know it's a sample. So if it's within that margin, and theta of n minus 1 is less than pi times margin, we could say to record the sample. And then we need to check and tune our samples per symbol. So we can say if a zero crossing occurs, then you could say that error equals your theta of n. Keep in mind all these thetas of n are wrapped to pi. Our theta of n equals wrapped to pi of whatever. That's your error function. And then of course, you just tune it, right? You adjust your samples per symbol. Right? And you repeat. And this should get all your samples. Yeah, any questions? I feel like this is kind of like a weird loop. Anything you guys want me to go over again, or just like talk about a little bit? Okay. One last thing. Actually, it's not important. Okay, so this is how you're going to implement and record samples. This way, you'll at least be able to find the right samples, right? But something we've not discussed yet is finding where your samples begin. Can you turn the camera, Victor? And this is what we call packet detection. So we know how to get, actually I'll come back to this, how to get the right samples, but how do we know, of course, when the packet begins? Let's talk about first the idea of a packet. We're not going to be continuously sending information. We're going to denote when we're sending information with what's called a packet and a packet header. So when we see this packet header, we know information is beginning, right? So we're not always transmitting, but our receiver is always listening, right? And of course, you can like standardize these kinds of things. This is like, there's so many protocols on packets and packet formats and all these things. But since you know when you design the packet, you know when it starts and when it ends once you do find it. And so packet's a very convenient way of transmitting information. And a common packet header, for example, would be like this. I'll talk about it in a second. But we encode a certain combination of bits, right? Or this is symbols. And if we know this, if we see this, we know our packet's beginning. Otherwise, it can just be noise and we're interpreting random bits. To understand this, we know about what's called a cross correlation. So a cross correlation is unfortunately a computationally expensive algorithm, but it's important in a lot of comms. And to give let's see, there are many ways you can explain this. I'm gonna try and do a couple approaches. cross correlation is an operation between two symbols. We'll denote with the same symbol as a convolution because, can you see the top of the board by the way? Right. Because the form of a cross correlation is very similar to that of a convolution, right? Where you have some f, some g, and they're time shifted. But in the case of a cross correlation, they're not time reversed versus a convolution is. And if you like draw what this kind of looks like, what you're doing is say we fix t, right? So say in t equals 1 case, you have say signal A, signal B. You multiply these two together and you integrate. T equals 2 case. You multiply these, say now this is shifted. You multiply these two together and you integrate. And what this generates is, used for all of time, I guess, is it's going to generate like peaks, right? So the cross correlation might look something like this, right? Or who knows what it would look like? Something like this, okay? Where this could be the cross correlation at time 1, time 2. This is not accurate, but hope you understand. That's the computational part, but something I also want to stress is a little bit more intuition on the underlying math. First thing you want to do is look at the form of this. And say your t is fixed, okay? You got f, some function f, times some function g, and you integrate that. Integrate meaning you add up. So if f was a vector of infinite length, and g was a vector of infinite length, you multiply all their entries together, and you add them all up. What is that? What operation is that?
A dot product.
It's a dot product, yeah. So you can say that a cross correlation is a dot product between two functions right. If you look at one specific time instance. What do we know about dot products? Dot products, one way to express a dot product would be the magnitude of the two functions multiplied together. And this kind of loses its meaning a little bit in continuous time because it can be infinite. But let's suppose it's not. Suppose it's bounded. The magnitude times a cosine, okay, of the angle between these two. That's what a dot product is. And the reason we really care about dot products is because of this cosine part. You have some constant, we'll call it A, times a cosine. And the cosine tells us its similarity. How well these two things line up together. And so, for example, if g is just f, g of t plus tau equals f, then that's the maximum, right? They're very similar, and you're going to have a spike in your cross correlation. You can look at this even in terms of deltas. You have, say, a point here at 1, and this is f, this is g, say this is at 2. So 2, say this is 1 and 1 for simplicity. Then we know that f of t times g of t plus tau, mixing up variables, f of tau, equals, well, when these two align, you're going to have a little spike. So that's when t equals -1. You're going to have a spike. All right. And yeah. And the reason we use a cross correlation in packet detection is because if we know our packet header and we do a cross correlation between our packet header and the signal, it's going to spike when we do find our packet header. So that's very convenient. Yes, this is an example of what a cross correlation could be. I didn't see this at first, so I just point this out. You have another delta right here, and so if you take the cross correlation between this and this, you get this kind of signal. The key thing to note is the spikes, right? So at 7, actually, like talking about in terms of numbers is not great, but when this aligns with here, say it's here and here, 4 and 12, or maybe it's something like that, or 5 and 12, some distance, we get a positive spike, right? Oh, you have another symbol here. That makes sense, okay. You can look through this and see that when it does align, it spikes. And the thing is, when it spikes, when it's perfectly aligned, it's going to be positive. And if this is if these are negative of this, it's going to be a spike in the negative direction. Okay, that's the key thing. You're going to have a large spike with the same magnitude, but maybe it's plus or minus. Okay. So keep this in mind, and we're going to come back to it in a second. So far, this is how we demodulate, right? We have our incoming signal. We get these kind of samples through demodulating. If we have a simple phase offset, we can get a tilted constellation diagram. You should have seen this in assignment 5, right? That's some angle theta. And through our Costas loop, it takes one point at a time and moves it down or up to the axis. So the thing is, the Costas loop does not know what's a 1 and what's a 0. So if you have a theta, which is above pi over 2, for example, this is going to be much closer. If this is a 1, then the 1 might be here and be put to the 0 side, or vice versa. And so even if your demodulation scheme is correct, you can have a bit error of 0 or a bit error of 100%. And so this is problematic a little bit. But of course, with a cross correlation and a known packet header, we can detect this. So here's a packet header. We pointed this out earlier. And if you do a cross correlation with an arbitrary set of bits, it's going to give you this kind of characteristic. And the reason we use this specific string is because people have done like their PhD thesis on this and stuff, but for when it's not aligned, you have very, very small cross correlations, right? But on the peak, it's a very large value. What we can do also is we can take 3 of these, stack them together. And having this exact configuration of bits is already very unlikely. Having three of them in a row is even more unlikely. So you can easily just stack it. Okay. So knowing that we can find our spikes by just looking at when these peak. We can also correct the issue we just talked about, right? Where we have a 180-degree phase shift. So if we have a 180-degree phase shift, then all these peaks would be negative, right? But still equal in magnitude. And so we know to just flip our bits if it's negative. And then you're gonna have 0% bit error. On your actual signal, it's gonna look something like this, right? We're gonna need to normalize it or something, but you're gonna see 3 peaks like this, and that's what you look for. So, yeah. Yeah, that's it. That's all I got. Thank you. Any questions?
What was the previous slide?
I don't think I want to talk about it. Yeah, so it's this thing that I just talked about. We're not doing the frequency estimation or, yeah, it's just to find the start of your packet. And yeah, that's okay. You don't worry about the last slide because your causes loop already fixes that, so that's okay. What's up?
I think I got lost like somewhere, but like, if we can like detect when starting, like, what's the issue with like detecting the timing? Wouldn't that give us like right when it starts?
So the timing is for finding the right samples. Because how do you know what samples to pick? Actually, let's go this way. Cross correlation is a very computationally expensive algorithm. If you were to do this on every single 400,000 samples that you collect, it's gonna take a long time.
Mac would explode.
Yes. Yeah. But you can pick the right samples first, get it down to 5,000, then perform the cross correlation and find where your packet starts. And it's much faster. That's a good question though. Yeah. Any other questions?